Allow your mind to quiet, let go of the day, and prepare to embark on a journey unlike any other. We are not traveling to a destination you can find on any map. Instead, we are descending through the deepest corridors of time, further and further back, past the first embers of human history, beyond the age of mammals, and into a world so ancient it feels like a dream. Our destination is the very beginning of the Earth, the primordial stage upon which the grand and epic story of the dinosaurs would eventually be written. Before we can meet these magnificent creatures, we must first witness the birth of their world. Our story begins in the cold, silent void of interstellar space. Approximately 4.5 billion years ago, the universe was already ancient, and in our quiet corner of the Milky Way galaxy, a vast and diffuse cloud of gas and dust, a nebula, lingered. This was the raw material of our solar system, enriched with heavy elements, forged in the heart of a long-dead star that had ended its life in a spectacular supernova. Within this cosmic cloud, the most patient and powerful force in the universe began its work: gravity. Slowly, imperceptibly at first, particles began to draw together. The cloud began to collapse inward on itself, spinning faster and faster as it contracted, flattening into a vast, rotating disk of matter around a growing, glowing central core. This core grew hotter and denser, until the pressure at its heart became so immense that nuclear fusion ignited. Our sun was born. Around this new star, the spinning protoplanetary disk contained all the leftover material, a chaotic swirl of rock, metal, and ice. Here in this cosmic nursery, the Earth began its violent formation. Through a process of gradual accretion, tiny dust grains, clinging together through static electricity, formed larger clumps. These clumps grew into pebbles, the pebbles into rocks, and the rocks into planetimals, small, primordial worlds, many kilometers in diameter. For millions of years, the early solar system was a cosmic shooting gallery. These planetimals, under the influence of gravity, constantly collided with one another, merging and growing in a process of runaway creation. With each monumental impact, the body that would become our Earth grew larger, and its interior grew hotter. The immense energy from these collisions, combined with the heat generated by the decay of radioactive elements trapped within its core, caused the entire planet to melt. Our world was born in fire, a glowing sphere of liquid rock, a seething ocean of magma. This earliest chapter of Earth's history is known as the Hadean Eon, a name derived from the mythological underworld, and it was a period of truly hellish conditions. For over 500 million years, the Earth's surface was a roiling, incandescent sea of lava. The planet was under a constant, heavy bombardment by the debris left over from the solar system's formation. Asteroids and comets of all sizes rained down from the sky, their impacts creating temporary craters in the molten surface, and sending up spectacular splashes of liquid rock. Volcanoes of a scale we cannot imagine today constantly erupted, venting the planet's interior gases and forming a thick, dense, and toxic first atmosphere. This blanket of gases consisted of water vapor, carbon dioxide, nitrogen, and sulfur compounds, but it was almost completely without the free oxygen that we depend on. The sky would have been a permanent, hazy, orange-brown shroud, and the air was utterly unbreathable. In the midst of this chaotic and fiery youth, our planet experienced a formative event of unimaginable violence, a collision that would define its future. According to the most widely accepted theory, a protoplanet, roughly the size of Mars, which scientists have named Theia, slammed into the molten Earth. The impact was not a direct hit, but a glancing blow, and the energy it released was staggering. Theia was completely obliterated, and a vast portion of Earth's own mantle was vaporized and blasted into orbit. This colossal cloud of superheated debris formed a glowing ring around our planet. Over thousands of years, gravity gathered the material in this ring together. It coalesced, cooled, and solidified, forming our constant companion in the night sky, the moon. This violent birth was critical for the future of life. The moon's gravitational pull stabilized the Earth's wobble, preventing chaotic swings in climate and giving us our predictable seasons. Its pull also created the ocean tides, a rhythmic force that would stir the coastal waters for billions of years to come. As the Hadean Eon continued, the heavy bombardment from space began to lessen. The solar system was clearing out its remaining debris with fewer catastrophic impacts. The planet could finally begin its long process of cooling. The surface of the magma ocean started to solidify, forming the first primitive crust. This crust was likely a thin, black, and brittle layer of volcanic rock, constantly being fractured and recycled back into the mantle by the intense geological activity below. As the planet's surface continued to cool, a crucial tipping point was reached. The immense quantities of water vapor that had been trapped as a gas in the hot, thick atmosphere could finally condense into liquid. And so, it began to rain. This was not a storm, but a planet-wide, relentless deluge that may have lasted for millions of years. Water poured from the hazy skies, cascading down the barren volcanic slopes of the new crust. It collected in the vast, low-lying basins, and over centuries, these basins filled, giving rise to the first oceans. These were not the blue oceans of today. They were likely hot, acidic, and due to the high concentration of dissolved iron, they would have had a murky, greenish hue. But they were, nonetheless, a global ocean of liquid water, the essential ingredient for life as we know it. The formation of these oceans marked the transition to the next great chapter in our planet's story, the Archean Eon. The Archean, which began around 4 billion years ago, was a time of increasing stability. The planet's crust thickened and matured through complex geological processes. Lighter rocks, such as granite, began to form and accumulate, creating the first small, stable blocks of continental crust. The ancient geological cores known as cratons. These were the first islands in the global ocean, the seeds of the continents to come. And it was in this new, more stable world, in the warm, shallow, nutrient-rich waters of the Archean oceans, that the greatest of all mysteries took place, the origin of life. We still do not know precisely how life began. Perhaps it was in a warm little pond, a primordial soup of organic chemicals, energized by lightning strikes and ultraviolet radiation from the sun. Or perhaps it was in the deep, dark ocean, in the chemical-rich water gushing from hydrothermal vents. But somehow, through processes of emergent chemistry, simple organic molecules linked together to form more complex structures. These structures eventually learned to replicate themselves, and at some point, one of these self-replicating systems became enclosed within a simple membrane, forming the first living cell. The earliest life on Earth was microscopic and simple. These were prokaryotes, cells without a nucleus, similar to modern bacteria. For hundreds of millions of years, they were the sole inhabitants of the planet, and they have left us their legacy, written in stone. In some of the oldest rocks on Earth, we can find fossilized structures called stromatolites. These are layered, mound-like formations, built up over thousands of years by vast communities of photosynthetic microbes called cyanobacteria. These microbes would form sticky mats that trapped particles of sediment. To avoid being buried, the microbes would continually grow upwards, creating layer upon layer, which eventually hardened into rock. These ancient stromatolites are the first visible evidence of life on our planet, a testament to the fact that once the stage was set, life took hold quickly and tenaciously. And within these humble microbial mats, a new biological process was being perfected, a process that would harness the power of the sun and release a waste product that would eventually transform the entire planet, paving the way for a world of greater complexity and grander scale. In the sunlit waters of the ancient Earth, a new kind of alchemy was being perfected within the tiny cellular walls of the cyanobacteria. This was photosynthesis, a process so elegant and so powerful that it would one day support nearly all life on the planet. It was a miracle of biochemistry, a way to build life not from the scarce chemical energy found in minerals, but from the most abundant and limitless resource available, the light of the sun. These microbes evolved a remarkable molecule, chlorophyll, a pigment that could capture the energy of a photon, a tiny particle of light that had traveled 93 million miles from our star. This captured solar energy became the power source for a sophisticated molecular machine that could perform a wonder. It could take a molecule of water, one of the most stable compounds in the universe, and split it apart. From this act of molecular cleavage, the cell would harvest electrons, the currency of energy, in the biological world. It would then use these high-energy electrons to combine molecules of carbon dioxide, which were abundant in the Archean atmosphere, into complex, energy-rich sugars. This was life's first great act of creation, the ability to spin sunlight and air into solid, life-sustaining matter. This new ability conferred an almost unimaginable evolutionary advantage. While other microbes had to eke out a living by slowly metabolizing chemicals found near volcanic vents or in mineral deposits, the cyanobacteria had a direct line to the boundless energy of the sun. They could make their own food anywhere the sun shone. This new power allowed them to proliferate on an unprecedented scale. They spread across the shallow seas of the entire planet, forming vast, green, living slicks on the surface of the water and building up their layered, reef-like stromatolite communities that grew ever larger and more numerous. But this revolutionary process, this great act of creation, had a byproduct, a waste product. For every molecule of carbon dioxide and water that was converted into life-giving sugar, a single, highly reactive molecule was left over and released into the environment. That molecule was oxygen. To our modern sensibilities, oxygen is the very essence of life, the gas we breathe with every moment. But to the anaerobic life that had dominated the Earth for the first 1.5 billion years of its existence, free oxygen was a deadly and corrosive poison. It was a violently reactive element that produced destructive molecules called free radicals, which would tear apart the delicate membranes and genetic material of any cell they encountered. The quiet, global flourishing of the cyanobacteria was therefore the beginning of the planet's first and greatest pollution event, a slow-motion, biological crisis that would unfold over 1 billion years and would ultimately poison the world for its incumbent inhabitants. For an immense stretch of time, however, the oxygen being steadily pumped out by these trillions of microbes did not build up in the atmosphere. It was immediately neutralized by the chemistry of the planet itself. The Archean oceans were a vast reservoir of dissolved iron leached from the planet's crust over eons. As the cyanobacteria released their oxygen into the water, each molecule would instantly collide with an iron atom and bind with it in the simple and relentless process of oxidation. This formed insoluble particles of iron oxide, the very same chemical compound as common rust. These microscopic particles of rust then began to drift down through the green murky water column in a constant, silent, and planet-wide rain. Over millions and millions of years, this rust accumulated on the seafloor in thick, heavy layers. This colossal, planetary-scale chemical event, the great rusting of the world, left an indelible and beautiful record in the Earth's geology. It created the Great Banded Iron Formations, or BFs. These are some of the most striking rocks in the entire geological record, thick sedimentary deposits composed of thousands of fine, alternating layers of dark, iron-rich minerals like hematite and magnetite, and lighter, iron-poor layers of silica-rich chert. Each delicate band is a page in the history of this ancient transformation. The layers may represent a seasonal cycle, with the iron-rich bands being laid down during the warm summers, when the cyanobacterial populations would bloom and produce vast quantities of oxygen, followed by the silica-rich bands being laid down in the colder winters, when the microbes were dormant. To stand before a great cliff face of banded iron is to witness a visual record of the Earth's oceans being slowly suffocated by the first breath of life. This process continued for nearly 1 billion years. The great oceanic sinks for oxygen were gradually, inexorably, filled. The last of the free iron was rusted out of the seas, and then a great tipping point in the history of our planet was reached. With nowhere else to go, the oxygen produced by the still flourishing cyanobacteria finally began to escape the surface of the oceans and accumulate in the atmosphere. This was the start of the great oxidation event. The sky began to clear as methane haze was broken down, and for the first time, the air itself began to fill with free oxygen. For the dominant anaerobic life on the planet, this was an apocalypse. Their world was being terraformed into an environment that was lethal to them. This event likely triggered the most profound mass extinction of all time, a holocaust that wiped out countless species of anaerobic microbes and forced the survivors to retreat into the dark, oxygen-free refuges of the world, like the deep ocean mud or geothermal springs, where their descendants remain to this day. But while this new oxygenated world was a death sentence for the old guard, it was a world of incredible opportunity for a new kind of life. In the crucible of this crisis, some microbes evolved enzymes that could not only neutralize the toxic effects of oxygen, but could harness its incredible reactive power. This led to the evolution of a new and vastly more powerful metabolic pathway, aerobic respiration. The process of breaking down a sugar molecule without oxygen might yield 2 units of cellular energy, but to break down that same molecule using oxygen could yield as many as 36 units of energy. It was the difference between the gentle flicker of a candle and the raging heat of a blast furnace. This new high-energy lifestyle, powered by oxygen, was the key that would unlock all future biological complexity. The rise of oxygen also set the stage for the next great evolutionary leap, the emergence of a new and profoundly more complex type of cell. For nearly 2 billion years, life had been the exclusive domain of simple prokaryotes, but then a new kind of cell appeared, one that was much larger, more robust, and contained a revolutionary degree of internal organization. This was the eukaryotic cell. This new design featured a central compartment, the nucleus, which provided a safe, protected vault for the cell's precious DNA. It also contained a host of other specialized, membrane-bound structures, called organelles, each performing a specific function, like a tiny city with its own factories, power plants, and transportation networks. The origin of this incredible cellular machine is a story of ancient partnership, a theory known as endosymbiosis. The narrative begins with a large ancestral host cell, likely an anaerobe, struggling to survive in the newly oxygenated world. One day, this host cell engulfed a smaller aerobic bacterium, but instead of being digested, the smaller bacterium was kept alive, taking up residence within the host. This was the beginning of a powerful symbiotic pact. The host cell provided the bacterium with a safe environment and a steady supply of nutrients. In return, the engulfed bacterium, which was an expert at using oxygen, became a dedicated internal power plant. It took the toxic oxygen from its surroundings and used it to burn fuel with incredible efficiency, producing a huge surplus of energy that it shared with its host. Over millions of years of coevolution, this internal partner became fully integrated, losing its ability to live on its own and becoming a permanent and essential part of the cell. This ancient, captured bacterium evolved into the organelle we now know and possess in every cell of our bodies, the mitochondrion. Every breath you take is a message to these ancient symbiotic partners, the descendants of a bacterium that was engulfed 2 billion years ago. A similar event later occurred in the lineage that would lead to plants, when a eukaryotic cell engulfed a photosynthetic cyanobacterium, which then evolved into the chloroplast. The eukaryotic cell is a chimera, a testament to the power of cooperation as a driver of evolution. With its protected DNA, its complex internal machinery, and its powerful mitochondrial engines, this new kind of cell had all the tools it needed to embark on the next great evolutionary experiment, building the first, simple, multicellular organisms, and paving the way for the visible, macroscopic life to come. As we move into the middle of the Jurassic period, approximately 174 million years ago, the world is a vastly different place from the arid supercontinent of the Triassic. The slow, inexorable process of continental drift has continued to tear Pangaea apart. The land masses have now separated into 2 great supercontinents, Laurasia in the north and Gondwana in the south, with the warm, shallow Tethys Sea flowing between them. This fragmentation of the land had a profound and beneficial effect on the global climate. With more coastlines and vast inland seas, moisture could penetrate deep into the continental interiors. The world became a warm, wet, and stable greenhouse, with little to no ice at the poles. This climate, combined with high levels of atmospheric carbon dioxide, created a paradise for plant life. The flora of the Jurassic was lush and abundant on a global scale. The landscape was dominated by vast, open forests of towering conifers, like the majestic Araucaria, groves of elegant, fan-leaved ginkgo trees, and thickets of palm-like cycads. The forest floors and the great open plains were not covered in grass, which had not yet evolved, but in immense unbroken prairies of ferns, horsetails, and club mosses. This incredible, planet-wide abundance of vegetation, this planetary buffet, was the essential fuel that would power the evolution of the largest and most magnificent herbivores the Earth has ever known. This was the golden age of the sauropods, these long-necked, plant-eating titans, which had their origins in the early Jurassic, now reached their zenith of size and diversity. To achieve such a colossal scale presented a host of profound biological and physical challenges. An animal's weight increases with the cube of its dimensions, while the strength of its bones increases only with the square of their cross-section. This meant that a truly gigantic animal risked collapsing under its own immense mass. It also needed to consume a phenomenal quantity of food, pump blood up a neck the length of a building, and avoid overheating its vast body. The sauropods evolved a suite of brilliant and interconnected solutions to these problems. Their skeleton was a masterpiece of lightweight engineering. Their vertebrae were not solid bone, but were hollowed out by a complex network of air sacs, a feature called pneumaticity. These air sacs were extensions of their incredibly advanced, bird-like respiratory system, which allowed for a one-way flow of air through their lungs, a far more efficient method of extracting oxygen than our own simple in-and-out tidal breathing. This system not only provided their massive bodies with the vast amounts of oxygen needed to fuel their metabolism, but it also made their skeletons remarkably light for their size, allowing them to grow to colossal proportions without being crushed by their own weight. Their feeding strategy was one of supreme energy efficiency. Their heads were tiny in proportion to their bodies, and their teeth were simple pegs or spoons, used only for stripping and gathering vegetation, not for chewing. This kept their heads light, a critical requirement for an animal with such an impossibly long neck. The neck itself was their greatest tool. It allowed them to be browsing cranes. A giant sauropod could stand in a single spot, and by sweeping its neck in a great arc, could graze on a vast area of low-lying ferns or reach high into the conifer canopy, all without having to move its gargantuan energy-consuming body. The real work of digestion was outsourced to their immense gut, a giant mobile fermentation vat where trillions of microbes would work for days to break down the tough plant matter they had swallowed whole. The Jurassic Plains were graced by a majestic parade of these gentle giants. There was the mighty Brachiosaurus, a true titan of the treetops. Its body was uniquely built, with front legs much longer than its hind legs, giving it a steeply sloped back. This posture held its neck at a high, upward angle, allowing it to browse on the crowns of the tallest trees, a food source utterly beyond the reach of any other contemporary herbivore. A different, but equally successful, design was seen in the diplodocids, like the famous Diplodocus. This was a creature of incredible length, with a long, horizontal body and a neck that it held low to the ground. It was a low browser, sweeping its neck from side to mow down vast swathes of ferns and cycads. Its tail was even longer than its neck, an impossibly slender, whip-like structure that it may have been able to crack at supersonic speeds, creating a thunderous sound to communicate with its herd or to deter a predator. Its cousin, a Patasaurus, often known by its more famous but junior synonym, Brontosaurus, was even more robust, a true power lifter of the Jurassic, with a massively thick neck and a powerful, stocky build. While the sauropods dominated the landscape through sheer scale, another great herbivorous dynasty, the Ornithischians, was perfecting the art of defense. This was the age of the stegosaurs. The most famous of all, Stegosaurus, was a large four-legged herbivore that roamed the same fern prairies as the great sauropods. Its back was adorned with a double row of large kite-shaped bony plates. These plates, once thought to be armor, were thin and filled with blood vessels, and were most likely used for display, a vibrant, colorful billboard to attract mates and intimidate rivals. For true defense, Stegosaurus wielded a weapon of formidable power. At the end of its muscular tail were 4 long, sharp, bony spikes. This weapon, the thagomizer, could be swung with lethal force, and the fossilized evidence of a punctured Allosaurus vertebra proves that it was a weapon they used with deadly effect against the great predators of their time. And the great predator of the late Jurassic, the undisputed king of its ecosystem, was Allosaurus. This was a large and powerful theropod, a hunter of giants. Its massive skull was a lightweight but strong latticework of bone, and its jaws were filled with long, sharp, serrated teeth that were constantly being replaced. Its arms were powerful, and its 3-fingered hands were armed with huge, hooked claws for grappling with prey. Allosaurus was the primary predator of the stegosaurs and the young or weak sauropods. It likely hunted with a combination of ambush and brute force, perhaps working in packs to harry the great herds, looking for an opportunity to isolate a vulnerable individual and bring it down with its devastating bite. It shared its world with other large carnivores, like the horn-nosed Ceratosaurus and the even larger and more robust Torvosaurus, ensuring that the lives of the great herbivores were ones of constant vigilance. This was the Jurassic world at its zenith, a stable, majestic ecosystem of titans, a world in a state of sublime and mighty equilibrium. Our journey now carries us across the threshold into the Cretaceous period, a vast expanse of time that began approximately 145 million years ago and would last for nearly 80 million years, making it the longest period of the Mesozoic era. This was an age of profound and continuous geographical change. The slow-motion fracturing of the great supercontinents, Laurasia and Gondwana, accelerated. Land masses that had been connected for eons were now finally sundered by new and widening oceans. This process of continental fragmentation had a dramatic effect on the planet. With more coastlines and a more active mid-ocean ridge system, global sea levels began to rise, eventually reaching the highest point in the last half-billion years. Vast, shallow, and warm epicontinental seas flooded the low-lying interiors of the continents, transforming them into a world of archipelagos and island continents. This geographic isolation would become a powerful engine of evolution, creating unique and distinct dinosaur faunas on each separate landmass. The climate of this new world was a stable and extreme greenhouse. Temperatures were high across the globe, and with little to no ice at the poles, lush, subtropical forests likely extended all the way into the Arctic and Antarctic circles. And in these warm, wet, and stable conditions, a quiet but momentous revolution was taking place at the very foundation of the food chain. For over 100 million years, the world's landscapes had been dominated by the ancient lineages of gymnosperms, the conifers, the cycads, and the ginkgos. But now, in the early Cretaceous, a new kind of plant appeared, the angiosperms, the flowering plants. This was a botanical innovation that would change the world forever. These new plants possessed a suite of powerful advantages over their gymnosperm cousins. They evolved the flower, a sophisticated and often beautiful reproductive structure designed to do something revolutionary, to entice animals into their service. By offering nectar as a reward, they co-opted a new and burgeoning group of insects into acting as dedicated couriers for their pollen, making their reproduction far more efficient than the wasteful wind-based pollination of the conifers. This sparked a great co-evolutionary dance, and the first true bees, butterflies, and moths appeared and diversified alongside their floral partners. The angiosperms also invented the fruit, a protective and often nutritious vessel for their seeds, which again enticed animals into dispersing their offspring far and wide, and they could grow and colonize disturbed land far more quickly than the slow-growing gymnosperms. Throughout the early and middle Cretaceous, these new, tough, and fast-growing plants began to take over the world's understory, creating new types of dense, scrubby habitats. This profound shift in the world's flora had a direct and dramatic impact on the great dinosaurian herbivores. In the northern continents, the great Jurassic sauropods and the plated stegosaurs, which were adapted to a world of open fern prairies and cycad groves, began a slow decline. Their world was changing beneath their feet, while the sauropod lineage would continue to thrive and produce new, even more colossal titans in the southern continents of Gondwana. In the north, a new dynasty of herbivores rose to prominence, one that was perfectly equipped to deal with the new, tougher vegetation. These were the ornithopods. The quintessential herbivore of the early Cretaceous was Iguanodon. This was a large, powerful, and incredibly successful dinosaur. It could walk on all fours to browse on low-lying plants, or rear up on its powerful hind legs to reach higher. Its mouth was a formidable cropping tool, with a sharp, toothless beak, and most importantly, the ability to chew its food with a complex grinding motion, an adaptation that gave it a huge advantage in processing the tough new angiosperms. For defense, it wielded a unique and iconic weapon, a conical sharp spike on each of its thumbs, a formidable dagger for fending off the great predators of its time. From these successful iguanodonts, an even more advanced group began to evolve, the hadrosaurs, or duck-billed dinosaurs. They perfected the art of chewing, evolving incredibly complex dental batteries, with hundreds of teeth packed into a single, ever-replacing, grinding surface, making them the most efficient herbivores the world had yet seen. As the ornithopods rose, the stegosaurs faded into extinction, and their role as the armored herbivore was taken up by a new and far more impregnable dynasty, the ankylosaurs. These were the ultimate living tanks. A creature like Sauropelta, from the early Cretaceous, was a low, wide, and immensely heavy animal. Its back and neck protected by a dense mosaic of bony plates and multiple rows of long, terrifying spikes that projected outwards from its body. This was an animal that was almost impossible to attack from above. With this changing of the guard among the herbivores, a new generation of predators evolved to hunt them. The allosaurs of the Jurassic were replaced by a new and even more terrifying family of giant theropods, the Carcharodontosaurids, the shark-toothed lizards. These were the true tyrants of the mid-Cretaceous. On the island continent that was South America lived Giganotosaurus, a predator of almost unbelievable size, a hunter that may have been even longer and heavier than Tyrannosaurus rex, and it was the apex predator in a world still home to colossal, 100-ton titanosaurs. In Africa, there was its cousin, Carcharodontosaurus, another giant with a massive skull filled with long blade-like, serrated teeth, perfectly designed for slicing through flesh. And in North America, there was Acrocanthosaurus, a formidable giant with a distinctive high ridge of spines running along its back. While these giants reigned as apex predators through sheer size and power, another, very different lineage of theropods was perfecting the art of sophisticated, cooperative hunting. These were the dromaeosaurs, the feathered raptors, a creature like Deinonychus from the mid-Cretaceous of North America was a revelation. Its discovery in the 1960s single-handedly overturned the old image of dinosaurs as slow, stupid, and lumbering brutes. Deinonychus was a sleek, fast, and agile predator with a large brain, forward-facing eyes for binocular vision, and a stiff, balancing tail. It was covered in a coat of complex, bird-like feathers, and on each foot it wielded its signature weapon, a large, sickle-shaped, retractable claw. Fossil evidence suggests they hunted in coordinated packs, a team of feathered assassins capable of bringing down prey much larger than themselves. This was the new world of the Cretaceous, a world of profound change and diversification. In the skies, the flying pterosaurs were now dominated by the advanced, short-tailed pterodactyloids, while the first true toothed birds fluttered through the forests. In the seas, the giant plesiosaurs, like Kronosaurus, were the apex predators, and on the fragmented continents, a new and dynamic ecosystem was taking shape, a world of duck-billed herds, of walking fortresses, of shark-toothed giants, and of intelligent, feathered pack hunters. The stage was now being set for the final and most spectacular act of the age of dinosaurs, A great oceanic extinction event around 94 million years ago would wipe out the mighty Dinosaurs, clearing the path for a new family of predators, the Tyrannosaurs, to rise to the throne. The world was on the cusp of the late Cretaceous, an age that would produce the most famous and fantastic dinosaurs of them all. Our journey now takes us into the final 15 million years of the Mesozoic era. The late Cretaceous was a world that in many ways would have looked surprisingly modern. The continents had drifted into a configuration that is almost recognizable to us. The Atlantic Ocean was widening, and the great island continent of Laramidia, which is now the western portion of North America, was a long, narrow landmass, bordered on the east by the warm, shallow waters of the western interior seaway. The climate was that of a hothouse, a warm, wet, and subtropical world, and the landscape was a lush tapestry of flowering plants. Great forests of magnolias, sycamores, and palms lined the banks of meandering rivers that flowed from the newly forming Rocky Mountains down to the coast. This was the stage, a vibrant and productive world, for the final and most spectacular act in the great drama of the dinosaurs. The dominant herbivores of this new world were the hadrosaurs, the duck-billed dinosaurs, who had now reached their evolutionary peak. They were the great herds of the late Cretaceous, the cattle of their age, and they existed in immense migratory herds that likely numbered in the thousands. Their success was founded upon their jaws, which contained the most sophisticated chewing apparatus of any reptile in history. Their batteries of hundreds of self-sharpening teeth were a perfect grinding mill for the tough, fibrous, and now abundant flowering plants. The most common of these was Edmontosaurus, a colossal animal that could reach up to 15 feet in length. Fossilized mummies of this dinosaur show it had a fleshy comb on its head, and it was the primary food source for the great predator of its time. But even more spectacular were the crested hadrosaurs, the Lambeosaurians. Their hollow head crests were some of the most bizarre and wonderful structures in the entire animal kingdom. A creature like Parasaurolophus, with its long, sweeping, trombone-like crest, was a living musical instrument. The crest was a network of hollow tubes, connected to its nasal passages. By exhaling through this complex, resonating chamber, it could produce deep, powerful, low-frequency calls that would have carried for many miles through the dense Cretaceous forests. These were the sounds of communication, used to keep the vast herds together, to warn of approaching danger, or to call for mates. Each species, from the helmet-crested Corythosaurus to the hatchet-crested Lambeosaurus, had its own uniquely shaped crest that would have produced its own unique call, a specific acoustic signature that allowed them to identify their own kind in a world filled with the calls of other giants. While the hadrosaurs found safety in numbers, other herbivores relied on the perfection of personal defense. The ankylosaurs, the living tanks, reached their ultimate form in Ankylosaurus itself. This was a creature built like a low, wide, impregnable fortress. Its entire back, neck, and head were encased in a solid shield of thick, interlocking bony plates, and even its eyelids were armored. But its true genius lay in its tail. The end of its tail was a massive, fused knob of solid bone, a colossal sledgehammer that it could swing with devastating force. The tail leading to this club was stiffened by interwoven tendons, turning it into a rigid, powerful handle. This was a weapon perfectly designed to be swung low to the ground, to shatter the ankle or leg of the only predator that dared to attack it. And vying for the title of the ultimate herbivore was the final great dynasty to emerge, the Ceratopsians, the horned dinosaurs. The most famous and the largest of these was Triceratops. This was a magnificent animal, 9 meters long and weighing up to 12 tons. Its head was a masterpiece of both offense and defense. It had a powerful, parrot-like beak for slicing through tough cycads and palms. For defense against predators, it wielded 3 formidable horns, 2 long, sharp horns over its eyes, and a shorter, robust horn on its nose. And sweeping back from its skull was its other signature feature, an immense solid shield of bone called the frill. This frill protected its vulnerable neck, but it was also a giant billboard for display, likely flushed with bright colors, to intimidate rivals and attract mates. It also served as a massive anchor for the incredibly powerful jaw muscles it needed to slice through the toughest vegetation. Triceratops was a formidable and successful animal, living in great herds, a walking bastion that even the greatest predator would have thought twice about attacking. And the great predator, the undisputed tyrant, king of this late Cretaceous world, was the culmination of 165 million years of theropod evolution. This was Tyrannosaurus rex. It was one of the largest terrestrial carnivores of all time, an animal of immense power and surprising sophistication. Its most devastating weapon was its head. The skull was over 1.5 meters long, but it was not just a block of bone. It was a complex and dynamic structure with fused nasal bones for strength in biting and kinetic joints that could absorb the shock of struggling prey. Its eyes were positioned forward on its face, giving it excellent, overlapping binocular vision and the depth perception of a hawk, a perfect tool for a hunter. And the olfactory bulbs in its brain were enormous, indicating a sense of smell so acute it could likely track its prey or a distant carcass over many miles. But it was the jaws and teeth that made Tyst Rex the ultimate predator. Its teeth were not the blade-like slicers of the Carcharodontosaurs that came before it. They were thick, serrated, railroad spikes of bone and enamel, designed not just for cutting flesh, but for punching through armor and shattering bone. The muscles that powered these jaws were immense, giving it the most powerful bite force of any land animal that has ever lived, a bite capable of generating over 12,000 pounds of pressure. This was not a delicate slicer, but a bone-crushing pulverizer. The infamous tiny arms, though small, were incredibly robust and muscular, and were likely used to hold struggling prey close to the body, away from the thrashing legs of a dying victim. Tyrannosaurus rex was the keystone predator of its environment, a hunter perfectly and terrifyingly evolved to take on the most dangerous and well-armed herbivores of all time, the hadrosaurs, the ankylosaurs, and the mighty Triceratops. This was the world of the late Cretaceous, in its final, glorious, and stable moment, a world of vast, communicating herds of duckbills, of powerful, horned ceratopsians, of impregnable, armored tanks, all living in a dynamic and balanced ecosystem presided over by the most powerful predator the land had ever known. This was the pinnacle, the final, beautiful, and terrifying expression of the age of dinosaurs. This world, so successful, so complex, and so enduring, had no reason to believe its time was coming to an end. But as this world turned, peacefully, beneath a familiar, star-filled sky, a silent and indifferent object, a tiny speck of light from the deep, cold darkness of space, was growing ever brighter, an object on a collision course with destiny, an emissary from the cosmos, carrying with it a message of absolute and fiery annihilation. Let us transport our minds to a single, ordinary morning, 66 million years ago, on the lush, subtropical coastal plain of the island continent of Laramidia. The sun is rising, its warm rays filtering through a canopy of broad-leafed magnolia and sycamore trees. A herd of the great hadrosaur, Edmontosaurus, moves slowly through a clearing, their low calls echoing in the humid air. Near the bank of a meandering river, a family of Triceratops is drinking, their immense horned heads lowered to the water. In the sky, a flock of the great pterosaur, Quetzalcoatlus, soars on wings the size of a small airplane. It is a world of sublime and majestic peace, a world utterly and completely unaware that it has less than an hour to live. For centuries, or perhaps millennia, an object born in the cold, dark depths of the solar system had been on a collision course with our planet. It was an asteroid, a colossal mountain of rock and metal, 10 kilometers, or 6 miles, in diameter. It was traveling at a velocity that is almost impossible to imagine, perhaps 70,000 kilometers per hour, a speed so great that it could cross the Atlantic Ocean in under 5 minutes. This object was not merely a rock, it was a vessel of almost inconceivable kinetic energy, an unstoppable bullet aimed at the heart of the Cretaceous world. In the final moments of its long journey, it entered the Earth's upper atmosphere, the air in its path, unable to get out of the way, was compressed into a glowing, superheated shell of plasma, many times hotter than the surface of the sun. For any dinosaur that happened to look up, it would have appeared as a second sun, a terrible, silent, and impossibly bright star that grew with terrifying speed, and then, in a fraction of a second, its journey was over. It struck the shallow tropical seas of what is now the Yucatan Peninsula in Mexico. The moment of impact was an event of pure, cosmic violence, an event that is arguably the single most violent day in the entire history of life on Earth. The asteroid, and a huge portion of the Earth's crust beneath it, did not shatter. It vaporized. The energy released was equivalent to the detonation of over 100 trillion tons of TNT, more than 1 billion times the combined yield of the atomic bombs used in the Second World War. It tore a hole in the fabric of the planet, a transient crater over 180 kilometers wide and 30 kilometers deep, laying bare the molten rock of the mantle below before the Earth's crust rebounded and collapsed to form the Chicxulub crater that we know today. The consequences of this single moment radiated outwards at the speed of physics. First, a seismic shockwave of a magnitude far greater than 12 on the Richter scale rippled through the planet's crust, triggering colossal earthquakes and volcanic eruptions on a global scale. The impact into the shallow sea displaced 1 trillion tons of water, creating a mega tsunami of almost unimaginable scale. A wall of water, initially perhaps over a mile high, blasted outwards from the impact site, scouring the coastlines of the Gulf of Mexico and sending giant waves racing across every ocean on Earth. A superheated air blast, a wave of incandescent pressure, flattened everything for 1,000 kilometers in every direction. But the most devastating of the immediate effects was a rain of fire. The impact had blasted trillions of tons of molten and vaporized rock high up into the sky, on trajectories that took it above the atmosphere and around the entire planet. As this material, now condensed into a thick swarm of tiny superheated glass beads called tektites, began to rain back down into the atmosphere, the friction of their passage heated the upper air to the temperature of a furnace. This created a brief but global thermal pulse of infrared radiation. The sky itself would have glowed a dull, menacing red. The heat was so intense that it would have cooked any animal that was not sheltered underground or deep underwater. And this global oven pulse had another, even more terrible effect. It instantly ignited the world's forests, continent-spanning wildfires. A true global firestorm began to rage, consuming the lush, green world of the Cretaceous in a planetary inferno. And the initial hours of fire, flood, and earthquake were only the beginning. The long, dark aftermath would be the true and final agent of extinction. The immense, black clouds of soot from the burning global forests, combined with the trillions of tons of pulverized rock dust and sulfur aerosols from the impact site, were blasted high into the stratosphere. There, they spread out, merging into a thick, impenetrable shroud that enveloped the entire planet. The sun was blotted out. A deep, unnatural, and absolute darkness fell over the earth, a darkness that would last for months, and a dim twilight that would persist for years. This was the beginning of the long impact, winter. With the sun's life-giving energy blocked, the planet's temperature plummeted. The warm, hothouse world of the Cretaceous was plunged into a state of freezing cold, and in this new world of darkness and cold, the very foundation of nearly all life on Earth was severed. Photosynthesis ceased. On the land, the plants that had miraculously survived the initial firestorm now withered and died in the dark and the frost. In the oceans, the phytoplankton, the microscopic floating plants that are the base of the entire marine food web, died off on a global scale. The result was a slow, agonizing, and inescapable ecological collapse. The great herbivorous dinosaurs, the mighty triceratops, the vast herds of hadrosaurs, the armored ankylosaurs, with their food source now gone, began to starve to death in their millions. Their immense size, for so long the key to their success, was now a fatal curse. Their huge metabolic needs, impossible to satisfy, in a dead and dying world. As the herbivores perished, so too did the carnivores. A Tyrannosaurus rex, the ultimate predator, would have found its world empty of prey, and it too, after stalking the dying plains for a time, would have succumbed to starvation. The entire glorious, complex ecosystem of the late Cretaceous unraveled from the bottom up, and to complete the devastation, the sulfur-rich rocks, vaporized at the impact site, created a prolonged and devastating period of intensely acid rain, which poisoned the soils and the surface of the oceans for years on end. When the dust finally settled, and the sun at last returned, it shone down upon a silent, broken, and empty world. Over 75% of all species on Earth had been wiped from existence. The ammonites and the great marine reptiles were gone from the seas. The pterosaurs were gone from the skies. And on the land, the long, magnificent, and unbroken 165 million year reign of the non-avian dinosaurs was over. The age of reptiles had ended in a day of fire and a long night of darkness and cold. The silence that fell upon the earth was a profound one, the silence of a fallen empire, the silence of a lost world. When the dust finally settled, and the sun at last broke through the clouds, it shone upon a different world. It was a silent, empty, and desolate planet. Over 75% of all species on Earth had been wiped from existence. The reign of the non-avian dinosaurs, a dynasty that had ruled the Earth for over 165 million years, was over. The age of reptiles had ended in fire and darkness. The silence that fell upon the Cretaceous world was a profound one, a silence that marked the end of an era and the end of some of the most magnificent creatures our planet has ever produced. The world that dawned at the beginning of the Paleocene epoch, 66 million years ago, was a ghost of its former self. The air was thin and clean again, but the planet was a landscape of devastation and silence. The great, lush forests of the late Cretaceous were shattered and burned, replaced by vast, monotonous carpets of hardy, fast-growing ferns, a fern spike visible in the geological record across the entire globe. The rivers ran thick with the mud and ash of a dead world, and on the land there was a profound and eerie quiet. The thundering footfalls of the great herds, the deep, resonant calls of the hadrosaurs, the terrifying roar of the tyrant king, all were gone forever. The world was an empty stage, a vacant throne waiting for a new ruler. But in the ruins of this fallen empire, life, in its most humble and resilient forms, had endured. The great extinction was a selective filter, and the survivors were those that possessed the right set of tools for weathering a global apocalypse. The first and most important of these tools was small size. A small body requires far less food to survive, a critical advantage in a world where the entire food chain had collapsed. The second was a generalist diet. The specialists, the animals adapted to eat only specific plants or prey, perished alongside their food source. The survivors were the opportunists, the creatures that could subsist on the scraps of a broken world, the insects and worms that burrowed in the soil, the fungi that thrived on the acres of rotting wood, the hardy seeds that lay dormant in the ground, and the very carcasses of the fallen giants. And the third great advantage was the ability to hide any creature that could burrow deep underground or find refuge in the heart of a freshwater river system, was shielded from the worst of the initial heat blast and from the subsequent prolonged cold of the impact winter. And among the survivors, our own distant ancestors, the mammals, were perfectly, if accidentally, equipped with all three of these traits. Throughout the entire age of dinosaurs, they had lived a life in the shadows. They were small, most no larger than a modern rat. They were often nocturnal, and many were burrowers, adaptations to avoid the notice of their giant reptilian rulers, and they were generalists, eating insects, seeds, and anything else they could find. This entire lifestyle, honed by 150 million years of suppression, was the perfect survival kit for the end of the world. As the great dinosaurs starved on the surface, our ancestors hunkered down in their burrows, waiting out the long night. When they finally emerged, It was into a world that was theirs for the taking. But they were not the only heirs to this new world. Many reptiles, too, had survived. The crocodiles and alligators, by living in the relative safety of freshwater rivers and having a slow, cold-blooded metabolism that allowed them to go for months without a meal, managed to endure. The turtles, with their protective shells and their ability to hibernate in the mud, also passed through the crucible. And most remarkably of all, the dinosaurs themselves had not entirely vanished. One special lineage of small, feathered theropods, which had already evolved the miracle of flight, had survived. These were the birds, their small size, their insulating coat of feathers that protected them from the cold, and their ability to fly vast distances to find scarce pockets of food, all gave them a crucial edge, and their toothless beaks may have been the key, allowing them to subsist on the seeds that were one of the few food sources left in abundance. The great dinosaurian dynasty had not been entirely extinguished. It had been pruned back to a single, hardy branch, a branch that would continue to flourish and diversify into our modern world. The early Cenozoic era, the age of mammals, was an age of incredible opportunity. With the dinosaurs gone, almost every major terrestrial ecological niche was now vacant, and the mammals, after 150 million years of waiting in the wings, rushed to fill the empty stage. The result was an explosive evolutionary radiation. In the 10 million years that followed the extinction, a geological blink of an eye, the humble, shrew-like survivors evolved into a dazzling and often bizarre array of new forms. There were the first large herbivores, like the hippo-like Coryphodon, and the first large mammalian predators, like the fearsome wolf-like Mesonyx. In the forests of Europe, giant, flightless terror birds, like Gastornis, a distant echo of their great theropod ancestors, briefly took on the role of apex predator. As the Cenozoic progressed, these early experiments gave way to the great lineages of modern mammals. The first primates, our own ancestors, took to the trees. The first horses, no larger than a small dog, appeared on the plains. The first true carnivores, the ancestors of dogs, cats, and bears, evolved their specialized shearing teeth. And in one of the most remarkable evolutionary journeys of all, a group of hoofed, land-dwelling mammals returned to the sea, evolving over millions of years into the first whales. The age of mammals had truly begun, a new world order, built directly upon the ashes of the old. And yet, as we stand in this new world, our world, we must understand that the legacy of the dinosaurs is not just in their absence, it is in their profound and living presence. Their story did not end 66 million years ago. It continues all around us. In every moment of every day, the incredibly efficient, one-way respiratory system that allowed the mighty Brachiosaurus to fuel its colossal body is the same system that allows a tiny hummingbird to beat its wings with impossible speed. The complex, insulating feathers that covered the body of a hunting velociraptor are the very same structures that paint the magnificent tail of a peacock. The parental care of a brooding oviraptorid dinosaur, sitting diligently on its nest of eggs, is the very same instinct that drives a songbird to build its nest in a garden tree. The dinosaurs are not gone. They are the most successful and diverse group of terrestrial vertebrates on the planet today. They are the 10,000 species of modern birds. Every time you see a sparrow on a branch, or hear an owl in the night, or watch a flock of geese fly south for the winter, you are bearing witness to the living, breathing, and thriving legacy of the great theropod dinosaurs. The dynasty never truly fell, it just grew wings. And so, our long journey through the deep and silent corridors of time comes to its final, peaceful close. We have traveled from the birth of a molten earth to the first spark of life. We have witnessed the poisoning and the greening of a planet. We have explored the strange, alien forms of the first animals and walked through the primeval forests of the Coal Age. We have survived the Great Dying, and we have spent 165 million years in the majestic, awe-inspiring, and terrifying world of the dinosaurs, a world that was their empire. Their story is a profound lesson in the nature of our planet. It is a tale of incredible success and of catastrophic failure, of the slow, grinding pace of evolution and the instantaneous violence of cosmic chance. It is a humbling reminder that no reign is eternal and that even the mightiest rulers of the earth can vanish in a geological instant. But it is also a story of connection. The fall of the dinosaurs was the single most important event that made our own mammalian world possible. Their story is the preface to our own. The history of life on this planet is a single, immense, and unbroken thread. It connects the stardust in our bones to the chemistry of the primordial sea, and it connects us, the inheritors of a fallen world, to the last, mighty Tyrannosaurus Rex that ever walked the earth. As you now drift into a deep and peaceful sleep, may you feel the quiet wonder of that immense, unbroken story and your own small but precious place within it. The invention of the eukaryotic cell was a moment of unparalleled biological potential. Yet, as we move forward from this great revolution, the Earth seems to enter a long period of evolutionary calm. This vast stretch of time, from roughly 1.8 billion to 800 million years ago, is often referred to by geologists as the boring billion. From the perspective of the fossil record, it can seem as though very little was happening. The stromatolite reefs, built by cyanobacteria, continued to thrive, but there were no dramatic new body plans, no great explosions of diversity. The world, it would seem, was holding its breath. But this apparent stasis was a deception. This was not a boring age, but a secret one. It was an era of critical, unseen preparation, a time when the fundamental genetic and biochemical groundwork for all future complex life was being meticulously laid down. In the quiet oceans, the new eukaryotic cells were slowly diversifying. The great lineages that would eventually give rise to the fungi, the plants, and the animals were going their separate ways, each exploring its own evolutionary path. The first simple experiments in multicellularity were taking place. These were likely just loose colonies of cells, or simple filaments of algae, organisms with no specialized tissues or organs, but within their genomes, a new and powerful genetic architecture was being assembled. The genes for cell adhesion, the biological glue that allows cells to stick together, were being perfected. The genes for cell-to-cell communication, which allows cells to coordinate their actions, were being refined, and the master control genes, the genetic architects that would one day direct the construction of complex bodies, were evolving. The boring billion was the long, slow, and quiet childhood of the animal kingdom. This long period of stability was finally shattered by the most severe and dramatic climate crisis our planet has ever experienced. Around 720 million years ago, at the beginning of a period known as the Cryogenian, the Earth was plunged into a deep freeze. The primary trigger for this event was likely the tectonic breakup of the first great supercontinent, Rodinia. As this immense landmass began to rift apart, it created thousands of miles of new coastlines. This led to increased rainfall over the land, which in turn accelerated the chemical weathering of continental rocks. This weathering process pulled enormous amounts of the heat-trapping greenhouse gas, carbon dioxide, out of the atmosphere, locking it away in marine sediments. As the planet's thermal blanket grew thinner, the global climate began to cool. Ice sheets began to form at the poles. As they grew, their bright, white surfaces reflected more and more sunlight back into space, a process known as the ice albedo feedback. This reflection of solar energy cooled the planet further, which caused the ice sheets to expand even more, which in turn reflected even more sunlight. A runaway feedback loop was initiated. The glaciers advanced from the poles, and the ice crept steadily towards the equator. Eventually, the entire surface of the planet became encased in a shell of ice, perhaps a kilometer thick, over the oceans. The world was transformed into a celestial snowball, a white and silent sphere drifting through the darkness of space. For tens of millions of years, the Earth remained in this frozen state. How could life, especially the newly evolved eukaryotes, possibly survive this global catastrophe? The vast majority of the planet's surface would have been sterile, but life is resilient. In the crushing darkness, beneath the global ice sheet, near volcanic hydrothermal vents, oases of warmth and chemical energy would have persisted, providing a sanctuary for microbial life. On the surface of the great glaciers, wind-blown dust could have accumulated in small pockets, absorbing sunlight and creating tiny, insulated pools of meltwater, which could have hosted their own microscopic ecosystems. And on the rare volcanic islands that may have poked through the ice, geothermal heat could have maintained small isolated lakes of liquid water. In these scattered and desperate refuges, life clung to a thread, waiting for the great winter to end. The end came not from the sun above, but from the fiery heart of the earth below. Throughout the long ice age, volcanoes continued to erupt, pumping a steady stream of carbon dioxide into the atmosphere. With the oceans sealed by ice, this greenhouse gas had nowhere to go. For millions of years, its concentration in the atmosphere built up, layer by layer. Eventually, it reached a tipping point. A super greenhouse effect took hold, and the planet began to warm. The thaw, when it came, was geologically instantaneous and incredibly violent. The snowball Earth was transformed into a hothouse Earth. As the colossal glaciers melted, they dumped a payload of nutrient-rich rock flour, which they had ground from the continents over eons, into the starved oceans. The world that emerged from this climatic crucible, the world of the Ediacaran period, was a renewed planet, its oceans now perfectly primed to fuel the first great flourishing of large-bodied, multicellular life. And flourish it did. For the first time, the fossil record reveals the imprints of a community of large, complex organisms. This was the Ediacaran biota, a menagerie of strange and wondrous creatures that populated the seafloor for nearly 100 million years. They were a bizarre collection of life's first drafts. There was Charnia, a creature that grew in the form of a feathery frond, anchored to the seafloor, in the deep, dark abyss, far from the reach of sunlight, proving it was an animal, not a plant. There were flat, segmented, quilt-like organisms, like Dickinsonia, which could grow to over a meter across and moved slowly across the seabed, absorbing nutrients through its skin. There were strange, three-lobed, disc-shaped creatures, like Tribrachidium, and slug-like animals, like Kimberella, which may have been one of the first to possess a true mouth and gut. This was an ecosystem built on principles that are alien to us. The vast majority of these creatures were soft-bodied, with no shells, no skeletons, no teeth, and no claws. Their biology was one of passive absorption, their bodies built with fractal, quilted patterns that maximized their surface area. For a time, it seemed that this was the future of life on Earth, a quiet, peaceful garden of strange, immobile forms. But this first great evolutionary experiment was doomed. As the Ediacaran period drew to a close, these strange creatures began to disappear from the fossil record. Their extinction is a mystery, but it coincides with a new and momentous development. In the very latest Ediacaran rocks, we begin to see the first evidence of a new kind of biology. We find the first fossilized burrows, evidence of animals actively moving through the sediment, and we find the first small shelly fossils, tiny, mineralized plates, spines, and shells. These two signs point to a single profound change in the rules of the game, the advent of active predation. For the first time, animals were beginning to hunt and eat other animals. This triggered the first great evolutionary arms race. The gentle, passive world of the Ediacarans was over. The need for defense, for shells and armor, and the need for new weapons, for claws and teeth, had now become the primary driver of evolution. A fuse had been lit. The quiet, preparatory ages were at an end, and the stage was now set for a biological Big Bang, a sudden and spectacular explosion of life that would lay the foundation for the entire animal kingdom to come. We have now crossed the great threshold from the long, enigmatic eons of the Precambrian into the Paleozoic era. Our journey brings us to the dawn of the Cambrian period, which began approximately 541 million years ago. The world is primed for a revolution. The oceans are oxygenated, the climate is warm, and a new ecological dynamic, the relentless pressure of predation, is now the driving force of evolution. For 3 billion years, life had been a story of microscopic cells, very briefly, a cast of strange, soft-bodied phantoms. But now, in a flash of geological time, that was all about to change. The stage was about to be filled with an almost unbelievable diversity of new and complex animal forms. This event is the Cambrian explosion, a biological Big Bang that would establish the blueprints for the entire animal kingdom in a geological instant. When we speak of an explosion in this context, we are not speaking of a single violent event, but rather of an unprecedented burst of evolutionary creativity that unfolded over a period of 10 to 25 million years. While this may seem like a long time to us, in the grand scale of Earth's history, it is a mere moment. In this narrow window, the fossil record, which had been sparse and enigmatic for billions of years, suddenly erupts with life. The true significance of this event lies not just in the number of new species, but in their fundamental diversity. It was during the Cambrian explosion that nearly all of the major distinct animal body plans, known to science as phyla, made their first appearance. The basic architectural designs for being an arthropod, a mollusk, a chordate, and dozens of other animal types were all laid down during this brief and fertile window of creative evolution. It was as if a master architect, after millennia of sketching simple huts, suddenly and furiously drew up the complete blueprints for every kind of building imaginable, from skyscrapers to cathedrals to cottages, all at once. Our knowledge of this incredible time comes from a few precious geological treasures, fossil sites known as Lagerstätten, where the conditions of preservation were so perfect that they have saved not just the hard shells and skeletons of animals, but also the delicate impressions of their soft parts, their gills, their guts, their antennae, and their eyes. The most famous of these is the Burgess Shale, a layer of black rock high in the Canadian Rocky Mountains. These fossils reveal a complete functioning ecosystem in stunning detail. An even older site in China, the Chengjiang Biota, shows that the explosion was already in full swing at the very beginning of the Cambrian, and a site in Greenland called Sirius Passet confirms that this was a truly global phenomenon. These sites are our windows into the Cambrian seas, and through these windows, we can see a world teeming with a menagerie of fantastic creatures. The most common and iconic of all were the trilobites. These arthropods were the definitive animals of the age, diversifying into more than 20,000 species. They were protected by a sophisticated, articulated exoskeleton, which they had to shed or molt in order to grow. They possessed complex, feathery gills for breathing, and their many legs allowed them to scuttle across the seafloor as scavengers, predators, or filter feeders. Their most revolutionary feature was their eyes. They had developed some of the first advanced visual organs on the planet, compound eyes made of many individual lenses, each lens uniquely carved from a single clear crystal of the mineral calcite. Through these crystalline eyes, the trilobites witnessed the dawn of the animal world. This new world of sight was also a new world of danger. The arms race between predator and prey was now in full swing, and it had produced its first great super predator. This was Anomalocaris, the abnormal shrimp. It was a giant for its time, some specimens reaching a meter in length. It was the undisputed apex predator of the Cambrian seas. It propelled itself through the water with a series of undulating fins, its two large stalked eyes giving it excellent vision to seek out its prey. At the front of its head, it wielded a pair of large spiny appendages, which it used to grasp and crush its victims, likely the hard-shelled trilobites. Its mouth was a circular ring of sharp, hardened plates, a terrifying device for breaking through the toughest of exoskeletons. Alongside these more recognizable creatures, the Cambrian seas were filled with a host of weird wonders, animals of such bizarre construction that they seem like beings from another planet, evidence of evolution, experimenting with body plans that would ultimately be evolutionary dead ends. There was the infamous Opabinia, with its 5 stalked eyes and a long, flexible proboscis that ended in a grasping claw, which it likely used to probe the sediment for food and deliver it to its rear-facing mouth. There was Wiwaxia, a slug-like animal, whose entire back was covered in a protective cloak of small armored scales and 2 rows of long, sharp, carbonaceous spines, a clear and dramatic response to the threat of Anomalocaris. And there was Hallucigenia, a creature so strange that for decades Scientists reconstructed it upside down and backwards, a testament to the truly experimental nature of Cambrian life. We now know it was a delicate, worm-like creature that walked on tiny stilt-like legs, with a row of sharp, defensive spines protecting its back. And amidst all this strangeness, all this armor and weaponry, a small, humble, and unassuming creature swam through the water. It was called Pikaia. It had no shell, no spines, no obvious defenses. It looked like a small, flattened ribbon, but it possessed one feature of profound importance for the future of life. Running along the length of its back was a stiff but flexible rod of cartilage called a notochord. This was the precursor to the backbone. Pikaia was a chordate, a member of our own phylum. Even earlier, in the Chengjiang fossil beds, we find creatures like Millicomingia, which not only had a notochord, but also a distinct head, gills, and a brain, making it one of the very first true vertebrates. In this distant, alien sea, our own most ancient relatives were quietly beginning their long journey, swimming in the shadows of the great invertebrate predators. The engine of this incredible, creative burst was a perfect storm of environmental, genetic, and ecological triggers. The newly oxygenated and nutrient-rich oceans provided the fuel and the building materials for larger, more complex bodies. A new genetic toolkit, the Hox genes, had evolved, providing the architectural instructions for assembling these new body plans. But the spark that ignited the explosion was ecological, the feedback loop of the evolutionary arms race. Predation drove the evolution of defensive shells. Shells drove the evolution of more powerful claws and jaws. The need to find prey and avoid predators drove the evolution of advanced senses like eyes, and eyes, in turn, drove the evolution of camouflage, new behaviors, and greater speed. It was a self-perpetuating cycle of innovation, a feedback loop that rapidly filled the empty seas with a complexity and a ferocity that life had never known before. The Cambrian explosion was the moment that our planet truly became the world of the animals. Imagine the world during the Ordovician period. The continents, still largely barren and lifeless, were arranged in a pattern unfamiliar to us. A great southern supercontinent, Gondwana, loomed over the South Pole, but much of the rest of the world's continental crust, including the landmasses that would become North America and Europe, was fragmented and located in the warm tropical latitudes. Global sea levels were incredibly high, flooding the continents and creating vast, warm, shallow inland seas that stretched for thousands of miles. It was in these sun-drenched, epicontinental seas that the next great chapter of life's diversification, an event known as the Great Ordovician Biodiversification Event, would unfold. This was not an explosion of new body plans, but an explosion of species, a great filling in of the ecological canvas that the Cambrian had sketched. The seafloor was transformed from a sparsely populated plain into a bustling, vibrant, and complex metropolis of life. For the first time, massive and intricate reef ecosystems began to grow. These were not yet the coral reefs of the modern world. They were constructed by a different cast of characters. The primary architects were strange, layered organisms called stromatoporoids, a type of sponge that created massive, stony, reef-building skeletons. The surfaces of these reefs were then encrusted by the delicate, fan-like, and branching colonies of bryozoans, the moss animals. And rising from the reef structure, like a dense submarine forest, were vast thickets of crinoids, the sea lilies. These were not plants, but animals related to starfish, with long, segmented stalks that anchored them to the bottom, and a crown of feathery, waving arms that they used to filter microscopic food particles from the gentle currents. The spaces between these reef builders were carpeted with life. The brachiopods, shelled animals that resembled clams, became so incredibly abundant that they are among the most common fossils of this period, and the first true corals, the tabulate and rugose corals, made their appearance, adding their own honeycomb and horn-shaped structures to these thriving, multi-layered communities. These reefs became the planet's first great biodiversity hotspots, providing food, shelter, and structure for thousands of new species. And floating in the sunlit waters above them were enigmatic, colonial creatures called graptolites. Their fossils look like tiny, carbonized saw blades, and for millions of years, these planktonic organisms were a key part of the oceanic food web. While the reefs became bustling cities, a new and formidable dynasty of predators rose to rule the open waters. The cephalopods, which had appeared in the Cambrian, now diversified into the undisputed apex predators of the Ordovician. The most dominant of these were the nautiloids, squid-like creatures that lived in long chambered shells. By carefully adjusting the amount of gas and water in these chambers via a tube called a siphuncle, they could achieve perfect neutral buoyancy, allowing them to hang effortlessly in the water column. The most fearsome were the giant orthocones, whose shells were not coiled, but perfectly straight and pointed. A creature like Camarasaurus was a true monster, with a shell that could reach a colossal 9 meters, or 30 feet, in length. It was a silent, jet-propelled hunter, moving by forcing water from its body, its many tentacles extended to snatch trilobites and other prey from the seafloor. And what of our own vertebrate ancestors? The jawless fish, the ignathans, were still humble, bottom-dwelling creatures. They diversified into many new forms, like the bizarre astrospus, with its head shield covered in star-shaped bony plates, but they were still jawless, clumsy swimmers, covered in heavy defensive armor. They were prey, living in the constant shadow of the great nautiloid predators, a testament to the fact that the future of the vertebrates was far from certain. For over 40 million years, this rich and stable Ordovician world flourished, but the history of life is a story of periodic catastrophe. As the Ordovician drew to a close, the great supercontinent of Gondwana drifted directly over the South Pole. This triggered a severe and prolonged ice age. As colossal ice sheets grew on the land, they locked up vast quantities of the world's water, and global sea levels plummeted. The warm, shallow inland seas, the very cradle of the Ordovician diversification, were drained away, exposing the magnificent reef communities to the air and destroying the habitats of countless species. This was the first pulse of the Ordovician Silurian extinction event, the second most severe mass extinction in the planet's history. The initial wave of death, caused by the chilling of the planet and the loss of habitat, was followed by a second. As the ice age waned, the glaciers melted and sea levels rose, flooding the continental shelves with cold, oxygen-poor water from the deep ocean, delivering a final lethal blow to many of the survivors. The world that emerged into the next period, the Silurian, was a world scoured by ice and extinction. But as the climate warmed once more, life began its slow recovery. The reefs rebuilt themselves, and the survivors began to radiate into the empty ecological niches. In the seas, the nautiloids now faced a new and fearsome competitor for the role of top predator, the eurypterids, or sea scorpions. These were giant aquatic arthropods, and some, like Pertragotus, were terrifying hunters, reaching over 2 meters in length, their powerful swimming paddles driving them through the brackish waters of the estuaries, their huge, crushing claws ready to snatch the fish that were now becoming more common. And it was among the fish that the most important evolutionary event of the Silurian took place. This was the evolution of the jaw. In a masterpiece of evolutionary repurposing, the first pair of bony arches that supported the gills in a jawless fish migrated forward, became enlarged, and developed a hinge. This simple modification was perhaps the most significant single innovation in the history of the vertebrates. It transformed the face of life. The jaw allowed an animal to bite, to grasp, to tear, and to chew. It opened up a universe of new predatory and dietary possibilities. The first jawed fish, the acanthodians, or spiny sharks, and the first of the great armored placoderms, appeared in the Silurian, a new and deadly force in the recovering oceans. But the most momentous event of all was happening in the quietest of places, at the boundary between the water and the land. For over 4 billion years, the continents had been barren, sterile wastelands of rock. But now, life was about to make its first tentative conquest of this new frontier. The pioneers were plants, evolving from green algae in the shallows. The first of these, a plant called Cooksonia, was a simple, leafless, rootless stalk, only a few centimeters high, a humble green shoot in a world of brown and gray. They could only survive in the dampest of places, forming a low green fringe at the water's edge. They were soon followed by the first animals to breathe air. These were arthropods, whose exoskeletons and jointed legs were perfectly pre-adapted for the challenges of life on land. The fossilized tracks of a millipede-like creature, and the fossilized remains of a tiny, air-breathing creature called Pneumodesmus, are the evidence of this monumental first step. A new world, a terrestrial ecosystem, had been born. It was small, it was quiet, and it was confined to the water's edge, but the greening of the continents had begun. Our journey now brings us across the threshold, into the Devonian period, which began approximately 419 million years ago. The world we enter is one of dual revolutions, a planet being transformed simultaneously on two separate fronts. In the oceans, the new and powerful innovation of the jaw was about to fuel an explosion of vertebrate diversity and the rise of the first true aquatic dynasty. And on the land, the humble, fringe-dwelling plants of the Silurian were about to embark on a full-scale invasion, a greening of the continents that would alter the atmosphere, the climate, and the very face of the Earth forever. The geography of this world was a patchwork of the great southern supercontinent of Gondwana and a smaller northern supercontinent known as Euramerica, surrounded by a vast global ocean. The climate was, for the most part, warm and hospitable, providing the perfect conditions for life's next great expansion. The conquest of the land was perhaps the greatest evolutionary challenge life had yet faced. The terrestrial realm was a hostile and alien environment. Without the buoyant support of water, gravity was a relentless crushing force. Without a constant bath of moisture, the threat of desiccation, of drying out and dying, was ever present. The air provided no protection from the harsh, unfiltered ultraviolet radiation of the sun, and reproduction, which for billions of years had relied on the medium of water, now required a new solution. To conquer this new world, the plants had to evolve a sophisticated new toolkit of adaptations. And they did so, with remarkable speed and ingenuity. The first great innovation was the perfection of a vascular system, an internal network of tubes that acted as both plumbing and structural support. Specialized tissues, called xylem, evolved to transport water and minerals from the ground up to the rest of the plant, while another tissue, phloem, distributed the sugars created during photosynthesis. This vascular system was reinforced with a strong, rigid organic compound called lignin, which allowed plants to grow tall and strong, defying the pull of gravity for the first time. They also evolved true, complex root systems that delved deep into the primitive soils, anchoring them securely and allowing them to tap into reliable sources of water and nutrients. And they developed leaves, broad, flat solar collectors, that dramatically increased their ability to capture sunlight. With these new tools, the humble, ankle-high green fringe of the Silurian exploded into the planet's first true forests. This was a strange and alien woodland, populated by plants unlike those of today. There were giant, tree-like club mosses, towering horsetails, and the first great tree ferns. But the true monarch of this new green world was a plant named Archaeopteris. It was the first plant to combine a strong, woody trunk, like a modern conifer, with a canopy of large, fern-like fronds. It could grow to heights of over 100 feet, and it formed the canopy of the first extensive, global forests in our planet's history. For the first time, a complex, multi-layered habitat existed on the land, a world of sunlit canopies, a deeply shaded understory, and a damp, rich layer of decaying leaf litter on the forest floor. These new forests had a profound effect on the planet. They created the first deep, organic soils. They stabilized the land against erosion, and through their immense photosynthetic activity, they began to draw down vast quantities of carbon dioxide from the atmosphere, an act of planetary engineering that would have dramatic consequences for the global climate. And in the shelter of these primeval woodlands, the arthropods thrived, with the first wingless insects and true spiders now colonizing the rich, damp world of the forest floor. While the land was turning green, the seas were turning into a kingdom of vertebrates. The Devonian was the undisputed age of fishes. The jawed fish that had first appeared in the Silurian now radiated into an incredible diversity of forms, becoming the dominant life forms in every aquatic ecosystem. The ruling dynasty of this era was the plecoderms, the armored fish. Their heads and bodies were encased in a shield of thick, bony plates, and their jaws were lined with razor-sharp, self-sharpening blades of bone. They were the tyrants of the Devonian seas, and their ultimate expression was the mighty Dunkleosteus. This was a true apex predator, a colossal fish the size of a school bus. Its armored head was 1.5 meters across, and its powerful jaws could snap shut with a force of 8,000 pounds per square inch. One of the most powerful bites in the history of life, it could shear straight through the bony armor of any other plecoderm that crossed its path. Alongside these armored giants, other, more modern fish lineages were flourishing. The cartilaginous fish, the sharks, were represented by swift, open-water predators like Cladozolac, and the bony fish, the Osteichthyes, were diversifying into the ray-finned fishes, the ancestors of almost all fish alive today. But it was the other branch of the bony fish, the lobe-finned fishes, that held the key to the next great evolutionary leap. Their fins were not thin rays of cartilage, but thick, fleshy, muscular lobes, supported by a robust and familiar pattern of internal bones. These fish, some of which had also evolved primitive lungs to gulp air from the surface, were perfectly pre-adapted for the challenges of shallow, stagnant, or drought-prone freshwater environments. And it was from this group of lobe-finned fishes that the first land-dwelling vertebrates would evolve. The most famous and perfect transitional fossil documenting this momentous event is a creature named Tiktaalik. Discovered in the Canadian Arctic, Tiktaalik was a true fishapod. It had the scales, gills, and fins of a fish, but it also had the flattened skull, mobile neck, and upward-facing eyes of an early amphibian. And most importantly, within its fleshy front fins, it had a robust set of limb bones, including a primitive wrist joint that allowed it to prop itself up in the shallows and move through the mudflats. From creatures like Tiktaalik, the first true tetrapods, or four-limbed vertebrates, evolved at the end of the Devonian. Animals like Acanthostega and Ichthyostega were still highly aquatic, with gills and fish-like tails, but they possessed 4 fully formed legs with distinct fingers and toes. They were the first vertebrates to walk, using their new limbs to navigate the tangled, plant-choked swamps that were now common at the water's edge. But this vibrant and revolutionary Devonian world, like the Ordovician before it, was brought to a close by a major extinction event. The late Devonian extinction was a prolonged crisis, with multiple waves of death stretching over millions of years. The causes were likely complex, but ironically, the very success of the new land plants may have been a primary trigger. By drawing down so much carbon dioxide from the atmosphere, the first forests may have caused a period of global cooling, and the new, rich soils they created washed into the oceans, carrying a flood of nutrients that would have caused massive algal blooms. The decay of these blooms would have stripped the oxygen from the shallow seas, creating vast, suffocating dead zones. This crisis was devastating for marine life, especially the warm-water tropical reef communities and the mighty plecoderms, which were driven to complete extinction. The great dynasty of armored fish was over, but the sharks, the ray-finned fish, and crucially, the newly evolved, four-limbed tetrapods in the shallows, all managed to survive. They inherited a world cleansed of its former rulers, a world of green continents and seas, ready for a new dynasty. The world we now enter is a world clad in green. The survivors of the late Devonian extinction, particularly the early four-limbed tetrapods, find themselves in a world perfectly suited for their semi-aquatic lifestyle. During the Carboniferous period, the continents of the Earth continued their slow-motion collision, gradually assembling into the final form of the great supercontinent, Pangaea. For millions of years, much of the planet's landmass was clustered around the equator, and this, combined with high sea levels, created a remarkably stable, warm, and humid global greenhouse climate. This was the perfect environment for the proliferation of vast coastal and lowland swamp ecosystems, the likes of which our world has never seen before or since. These were the great coal forests of the Carboniferous. To journey into one would be to enter an alien and majestic world. The air was thick, warm, and heavy with moisture, and the rich, earthy smell of damp vegetation and decay. And this atmosphere was fundamentally different from our own. The incredible productivity of these vast, global swamps, combined with the fact that much of the dead plant matter was buried in the stagnant, oxygen-poor water before it could fully decompose, led to a dramatic alteration of the air itself. With so much carbon being buried, instead of being released back into the atmosphere through decay, the oxygen produced by the endless photosynthesis of these forests built up to unprecedented levels, reaching a concentration of perhaps 35%. This hyperoxic atmosphere had a profound effect on the life within it, supercharging metabolisms and allowing life, especially those creatures that breathed air, to achieve gigantic proportions. The flora of these swamps was strange and wonderful. The canopy was not formed by the familiar trees of our time, but by ancient and primitive lineages. There were the giant club mosses, like lepidodendron, the scale tree. It grew to heights of over 40 meters, or 130 feet, but its trunk was not made of true wood. Its bark was covered in a beautiful diamond-like pattern, the fossilized scars left behind by fallen leaves. Its base was a strange forking root system called stigmaria, and its crown was a simple tuft of grassy branches. Densely packed thickets of giant horsetails, called calamites, grew like colossal bamboo, their ribbed and jointed stems reaching high into the humid air, and the understory was a nearly impassable jungle of giant tree ferns, their great fronds unfurling in the deep, perpetual shade. For millions of years, these plants flourished and died, falling into the swamp waters and accumulating in thick layers of peat. Over geological time, these layers were buried and compressed, their organic matter slowly transforming into the vast seams of coal that power our modern world, each piece a dark, fossilized remnant of the ancient Carboniferous sun. This oxygen-rich atmosphere, combined with the lack of any large vertebrate predators in the air, created a golden age for the arthropods. They grew to sizes that seem the stuff of nightmares today. The air above the swamps was patrolled by the griffinfly, Meganura. This was an insect that looked like a dragonfly, but it possessed a wingspan of over 75 centimeters, or 2.5 feet, the size of a modern seagull. It was a swift and voracious aerial predator, its huge compound eyes scanning for other flying insects, and moving through the damp, fern-choked undergrowth was the colossal myriapod, Arthropleura. This armored, segmented creature, a distant relative of modern millipedes, could reach a length of over 2.5 meters, or 8 feet, the largest land invertebrate of all time. It was a gentle giant, a herbivore that fed on the rich, decaying plant litter of the forest floor, its hundreds of legs carrying it like a living armored train through the primeval world. The forest litter was also home to giant scorpions like Pulmonoscorpius, the breathing scorpion, a formidable predator nearly a meter in length. In this world of giants, the vertebrates were also thriving. The Carboniferous was the great age of amphibians, the early tetrapods that had survived the Devonian extinction, now radiated into a stunning diversity of forms, becoming the dominant terrestrial and freshwater vertebrates. Their very biology, with their permeable skin that needed to be kept moist, and their jelly-like eggs that had to be laid in water, made them perfectly suited to the endless, watery world of the coal swamps. They became the apex predators of their time. Creatures like Eriops, a large, powerfully built amphibian with the stocky build of a crocodile and a wide, flattened skull full of sharp teeth, lurked in the murky shallows, ambushing fish and other tetrapods. Other amphibians took on even stranger forms, like the bizarre Diplocaulus, with its wide, boomerang-shaped head that may have acted as a hydrofoil, allowing it to swim against the current. Still others became long and serpentine, losing their limbs entirely to slither through the water and mud. For tens of millions of years, this was the established order. The amphibians were the rulers of the great global swamp. But even as the amphibians were at their peak, a small, and seemingly insignificant group of them was developing a biological innovation so profound that it would change the course of life on Earth forever. The amphibians were masters of the swamp, but they were prisoners of the water, forever chained to it for the act of reproduction. The new innovation was a way to break those chains. This was the evolution of the amniotic egg. This was a revolutionary invention. It was a private, self-contained nursery, a personal ocean for a developing embryo. A tough, leathery outer shell protected it from drying out and from physical damage. Inside, a series of complex membranes provided a complete life support system. The amnion was a fluid-filled sac that surrounded the embryo, protecting it from shock. The yolk sac was a rich, nutritious food supply, and the allantois was a special sac to store waste products. For the first time, a vertebrate could lay its egg on dry land, far from the nearest pond or stream. The conquest of the continents could now truly begin. The appearance of this amniotic egg marked the great schism in vertebrate evolution. The first amniotes, which appeared in the late Carboniferous, quickly diverged into two great lineages that would define the future of terrestrial life. The first of these were the synapsids. Their skulls were characterized by a single opening behind the eye socket. This seemingly minor anatomical detail is of profound importance, because this was the lineage that would eventually, after a long and complex journey, give rise to the mammals and to us. The other great lineage was the sauropsids, which included all the other reptiles. This was the lineage that would eventually produce the lizards, the crocodiles, the turtles, and most importantly for our story, the dinosaurs. As the Carboniferous gave way to the Permian period, some 299 million years ago, the world began to change once more. The slow collision of the continents was finally completed, forming the colossal supercontinent of Pangaea. The formation of this single, vast landmass created a drier and more seasonal global climate. The great global coal swamps began to shrink and retreat. This new, drier world put the amphibians at a disadvantage, and it was the newly evolved amniotes that were perfectly poised to take over. And it was our own distant relatives, the synapsids, that rose to become the dominant land animals of the early Permian. This was a world ruled by sail-backed predators like Dimetrodon. This was not a dinosaur, but one of our own kin, a powerful carnivore whose magnificent sail was likely a sophisticated device for regulating its body temperature. It was the apex predator in a world ruled by the Synapsid dynasty. This new world order seemed absolute and destined to last, but the very existence of the supercontinent was creating geological and climatic stresses that were slowly building towards a breaking point, a planetary fever that would result in the greatest biological crisis in the entire 4.5 billion year history of our planet. The early Permian was not a world of dinosaurs. It was a world dominated by creatures that are often mistakenly called mammal-like reptiles. A prime example, and the top predator of its day, was Dimetrodon. Although it looked like a reptile, it was in fact an early synapsid, more closely related to you and me than to any dinosaur. It was a powerful, four-legged carnivore with a large skull filled with differentiated teeth, including sharp canines, a distinctly mammal-like trait. Its most famous feature was the magnificent sail-like fin on its back, supported by long spines extending from its vertebrae. This sail was likely a sophisticated thermoregulatory device, a kind of biological solar panel used to absorb heat and warm its body quickly in the morning sun. It shared its world with other sail-backed synapsids, like the herbivorous Edaphosaurus. For millions of years, this was the established order. The synapsids were the rulers of the Earth, but the stability of the Permian world was an illusion. Deep within the planet, geological forces were building towards a catastrophe, a planetary fever that would bring about the most profound biotic crisis in the entire history of our world, an event that would come to be known as the Great Dying. The late Permian was the zenith of the age of synapsids. The world had recovered from the climatic shifts that marked the end of the Carboniferous, and life had adapted to the new realities of the great supercontinent, Pangaea. The global climate was one of extremes. with vast, arid deserts in the continental interior where rainfall was scarce, and powerful, seasonal mega-monsoons that lashed the coastlines of the single great ocean, Panthalassa. In this challenging world, our distant relatives, the synapsids, had produced their most advanced and formidable forms. The sail-backed creatures of the early Permian were gone, replaced by a new dynasty of faster, more efficient, and more mammal-like reptiles. The role of apex predator had been taken up by the fearsome Gorgonopsians, a creature like Inostrantvia from the late Permian of what is now Russia, was a terrifyingly powerful hunter. It was the size of a large tiger, but it was built with a sleek, muscular grace. Its legs were positioned more directly under its body than those of its ancestors, allowing for a more sustained and efficient mammal-like gait. Its skull was long and powerful, but its most devastating feature was a pair of colossal, saber-like canine teeth, which it used to inflict devastating wounds on its prey. They were the undisputed rulers of the Permian food chain, and their prey was abundant. The most successful herbivores on the planet were the Dicynodonts, a diverse group of tusked, beaked synapsids. They ranged in size from small, burrowing creatures, like Divatodon, which lived in complex underground galleries, to the large hippo-sized Lystrosaurus, a bulky, powerful herbivore that likely roamed the plains in vast herds. They were immensely successful. The cattle of the Permian, and their strange turtle-like beaks, were perfectly adapted for cropping the tough, arid vegetation of the time. This was a complex and mature ecosystem, filled out by other groups like the large, heavily armored parasaur reptiles, such as Scutosaurus. For millions of years, this was the established order, a world ruled by the Synapsid dynasty. It seemed eternal, absolute, and unshakable, but it was all about to be erased. The catastrophe began, not with a bang, but with a slow, deep sickness from within the planet itself, deep beneath the crust. In the region of modern-day Siberia, a colossal plume of superheated rock from the Earth's mantle began to rise. As this mantle plume reached the base of the crust, it spread out, melting the rock, and creating an immense reservoir of magma. The pressure built until finally, around 252 million years ago, the crust gave way. The ground split open, not in a single volcanic cone, but in a vast, sprawling network of fissures that tore across the land for thousands of miles. This was the birth of the Siberian Traps, a flood basalt event of almost unimaginable scale. For the next several 100,000 years, a relentless and almost continuous eruption poured colossal floods of fluid, basaltic lava, out onto the surface of Pangaea. Curtains of fire, miles long and hundreds of feet high, lit up the Permian sky. Rivers of molten rock, wider than any river of water, incinerated the sparse conifer forests and buried the landscape under a thick, black shroud of volcanic rock. The eruptions were so vast that they would ultimately cover an area of 7 million square kilometers, larger than the continent of Australia, in a layer of basalt that was, in some places, over 6 kilometers thick. This eruption initiated a cascade of environmental collapses that would assault the entire global biosphere. The first blow was atmospheric. The volcanoes belched immense quantities of sulfur dioxide and ash into the stratosphere, which created a veil that blocked sunlight, triggering a brief but devastating volcanic winter and causing intense, ecosystem poisoning acid rain to fall across the globe. But this was merely a prelude. The main event was a thermal one. The eruptions also released a staggering volume of carbon dioxide. To make a planetary crisis infinitely worse, the Siberian crust was home to one of the world's largest reserves of coal and natural gas, the buried remains of the ancient Carboniferous swamps. As the magma burned its way through these vast fossil fuel deposits, it cooked them, releasing their stored carbon, a cataclysmic pulse of carbon dioxide and methane, directly into the atmosphere. A runaway greenhouse effect took hold. The brief volcanic winter was replaced by a suffocating global fever. Average global temperatures soared, perhaps by as much as 10 degrees Celsius. The equatorial regions became lethally hot for most forms of life. The oceans absorbed this heat, and their chemistry began to break down. The warm water could hold less oxygen, and the normal ocean currents that circulated oxygen to the depths stagnated and stopped. The deep oceans became vast, suffocating, anoxic zones. At the same time, the colossal amount of carbon dioxide dissolving into the water formed carbonic acid, turning the oceans acidic. This corrosive water made it impossible for marine organisms to build their shells and skeletons. The great reefs, the brachiopods, the trilobites, and the plankton at the very base of the food chain were literally dissolved by the changing chemistry of the seas. And then, as the final, horrifying chapter of the extinction unfolded, the anoxic oceans became a breeding ground for anaerobic, sulfate-reducing bacteria. These microbes thrived in the poisoned water, and in doing so, they released vast quantities of toxic hydrogen sulfide gas. The deep oceans began to turn into a poisonous, purple soup. Eventually, this deadly gas would have bubbled up to the surface and been released into the atmosphere, poisoning terrestrial life directly and tearing apart the Earth's protective ozone layer, allowing lethal UV radiation to flood the surface. The result was the Great Dying, the most profound and devastating biotic crisis in the history of complex life. The statistics are almost incomprehensible. Up to 96% of all marine species and 70% of all terrestrial vertebrate species were driven to extinction. The trilobites, survivors of 2 previous mass extinctions, were gone forever. The mighty gorgonopsians, the diverse dicynodonts, the Parasaurolophus, almost the entire magnificent fauna of the Permian was erased. The world that emerged into the early Triassic was a desolate, empty, and broken planet. It was a world where the forests had died, leaving a fossil record marked by a spike of fungal spores, a planet dominated by rot. It was a hot, arid ghost world, haunted by the memory of the life that it had lost. And in this silent, empty world, a single, unassuming survivor became, for a time, the most successful animal on Earth. This was Dinosaurs, this pig-sized, herbivorous synapsid, with its strange tusks and beaked face, had somehow made it through the fire and the poison. Its burrowing lifestyle may have protected it from the worst of the heat, and its efficient respiratory system may have helped it survive in the low oxygen atmosphere. In the immediate aftermath of the Great Dying, Dinosaurs became so numerous that its fossils account for up to 95% of all land vertebrates in some early Triassic fossil beds. Its lonely dominance was not a sign of its strength, but a symptom of a planet that had been wiped almost completely clean. The Synapsid dynasty was shattered. The old world was dead, but in this great emptiness, there was also a great opportunity. For the few, humble reptiles that had also survived the cataclysm, the world was now theirs for the taking. The stage was now set for a new dynasty to rise from the ashes. But in Nenet's time, the dawn of the Mesozoic era, the Triassic period, was a harsh and challenging time. The great supercontinent of Pangaea, a single colossal landmass, baked under a relentless sun. The climate was hot and dry, with vast, arid deserts dominating the continental interior. For millions of years, the planet's ecosystems were broken, impoverished shadows of their former glory. The lush, diverse forests of the Permian were gone, replaced by hardy, opportunistic plants, like quillworts and seed ferns, tough pioneers in a damaged world. In this challenging new era, the story of life was a story of recovery. The initial, lonely dominance of the herbivore Dinosaurs was a sign of this ecological devastation, but as the millennia crept by, the planet slowly began to heal. Conifer forests began to spread across the recovering landscapes, and with this returning vegetation, new forms of animal life began to evolve and diversify, competing to fill the countless empty niches. The synapsids, our own distant kin, had been the great victims of the extinction, their dynasty shattered. But they were not entirely extinguished. A particularly advanced and resilient group, the cynodonts, had made it through the fire. In the Triassic, they underwent a quiet renaissance, not as the world's rulers, but as masters of survival, becoming progressively more mammal-like with each passing generation. Creatures like Thrinaxodon, a small, ferret-sized animal from the early Triassic, lived in complex burrows, a behavior that likely helped its ancestors survive the extinction. Its fossils show a host of advanced features, from a complex, chewing dentition to a secondary palate in the roof of its mouth that allowed it to breathe while it ate, a critical adaptation for a more active metabolism. Pits on its snout suggest it had sensitive whiskers, and perhaps a coat of fur. Later, larger forms, like the wolf-sized Synagnathus, became formidable predators in their own right. These were the ancestors of all mammals, including ourselves, adapting to a new role in a new world, often becoming nocturnal, living in the shadows of a new and rising dynasty of reptiles. The great evolutionary vacuum of the early Triassic was ultimately filled by the sauropsids, and one group in particular radiated with spectacular success: the archosaurs, the ruling reptiles. They were perfectly suited for the hot, dry world of the Triassic, and they quickly diversified, splitting into two great lineages whose competition would define the period. The first, and for a very long time, the most dominant of these lineages, was the Pseudosuchia, the crocodile-line archosaurs. For most of the Triassic, these were the true rulers of Pangaea. They evolved into a stunning array of forms. The rivers and lakes were patrolled by the phytosaurs, giant, semi-aquatic predators that looked and behaved almost exactly like modern crocodiles. The land was home to the atosaurs, like Desmatosuchus, which were like walking castles. These were large herbivores, completely encased in a heavy armor of bony plates, with a pair of huge, sharp horns curving out from their shoulders for defense. The role of the top terrestrial predator in the Triassic was not held by a dinosaur, but by the Rossuchians, a group of fearsome, quadrupedal, and sometimes bipedal crocodile-line carnivores. A creature like Postosuchus was a 9-meter-long terror, the apex predator of its ecosystem in the late Triassic. With its massive skull, blade-like teeth, and powerful build, it was the undisputed king of its world, a world where the dinosaurs were only just beginning to find their footing. The other great archosaur branch was the Avametatarsalia, the bird-line archosaurs. This was the lineage of speed and agility. While the Pseudocians were evolving into heavy, powerful tanks and crocodile-like ambush predators, this group was perfecting a lightweight, bipedal body plan. Early members, the ancestors of both the pterosaurs and the dinosaurs, were small, fleet-footed creatures like Marsuchus. They were built to run, with long, slender hind limbs and a specialized, hinge-like ankle joint that gave them a more efficient forward and backward stride. For millions of years, they occupied the niches of small insect and lizard eaters, darting through the undergrowth, living in the shadows of the larger, more powerful Rossuchians. And then, in the late Triassic, around 231 million years ago, in the temperate and forested southern region of Pangaea, that we now know as Argentina and Brazil, a new kind of animal evolved from these small bipedal ancestors. This was the birth of the first true dinosaurs. Their secret was a subtle but profound anatomical innovation in their hip. The socket for the leg bone, the acetabulum, was now fully perforated, a complete hole. This allowed their legs to be positioned directly and vertically beneath their bodies in a pillar-erect stance. This was a far more efficient and powerful posture for walking and running than the semi-sprawling gait of their Pseudocian rivals, and it was the key to their future success. These first dinosaurs were not the giants of later ages. They were modest pioneers. There was Eoraptor, the dawn raider, a small, slender creature, only about a meter in length. It was a nimble, bipedal carnivore, or omnivore, a perfect example of the primitive ancestral dinosaur body plan. A contemporary, Heretosaurus, was a more formidable predator, reaching up to 6 meters in length. It had a long skull full of serrated teeth, and powerful, 3-fingered hands with sharp claws for grasping prey. And alongside these first carnivores, the first herbivorous dinosaurs also appeared, early sauropodomorphs like Eodromeus, which were also small and bipedal. But we must understand that the late Triassic was not yet the age of dinosaurs. It was a fiercely competitive world. These first, humble dinosaurs had to contend with the reigning Pseudocian kings like Postosuchus. They had to avoid the armored etosaurs, and they shared the world with the advanced mammal-like cynodonts. The dinosaurs were just one of several successful groups of animals, a promising but not yet dominant experiment. Their time on the throne was not yet guaranteed. The supercontinent of Pangaea, the stage for this great drama of recovery and competition, was itself growing unstable. The immense geological forces that had once pushed the continents together were now beginning to pull them apart, and this tectonic strain was building towards another great planetary crisis, a final extinction event that would clear the board one last time and give the dinosaurs the world. Largest land animals of all time. Let us pause for a final moment in the world of the late Triassic, some 201 million years ago. It is a world teeming with life, a biosphere that has over 50 million years painstakingly rebuilt itself from the ashes of the great dying. In the ferny undergrowth, a small, bipedal dinosaur like Colophysis darts through the shadows, its sharp eyes scanning for insects and small lizards. In the rivers, a giant, crocodile-like phytosaur lurks beneath the surface, waiting for a thirsty herbivore to venture too close. On the plains, a herd of armored, pig-snouted atosaurs digs for roots, their bony plates glinting in the sun, and watching over this entire ecosystem is the apex predator, the mighty Rauisuchian, Postocius, the undisputed ruler of its domain. This was the established order, a world of checks and balances, a world where the dinosaurs were just one of several successful evolutionary experiments. But the geological clock was ticking, and this entire complex world was on the verge of being erased. The great supercontinent of Pangaea, which had defined the planet's geography for so long, was beginning to tear itself apart. Deep beneath the crust, a colossal plume of superheated mantle was pushing upwards, stretching the lithosphere to its breaking point. A great rift began to form, a jagged, spreading wound that snaked through the very heart of the supercontinent, a scar that would one day, after millions of years, widen to become the Atlantic Ocean. As the crust pulled apart, it thinned, and magma from the deep earth found a pathway to the surface. This was the beginning of the Central Atlantic Magmatic Province, or Camp, the second great flood basalt event of the Phanerozoic eon. The eruptions were not a single, explosive event, but a series of colossal, effusive outpourings of lava that occurred in pulses over a period of some 600,000 years, across an area that now encompasses 4 continents, from North and South America to Africa and Europe. The ground split open. Vast fissures, hundreds of kilometers long, ripped through the Triassic landscape, creating not volcanoes, but great, roaring curtains of fire. From these fissures, a truly staggering volume of fluid, basaltic lava poured out, flooding over the land in great black sheets, incinerating the conifer forests, and burying millions of square kilometers under a thick, volcanic blanket. The environmental consequences of this immense volcanic event were catastrophic, and they came in a series of devastating waves. The first blow was a sudden and paradoxical cold snap. The eruptions blasted a colossal amount of sulfur dioxide into the stratosphere. This gas reacted with water vapor to form a fine, reflective haze of sulfate aerosols, which shrouded the entire planet, blocking out a significant portion of sunlight. This triggered a brief but intense volcanic winter. Global temperatures plummeted, and the warm, greenhouse world of the Triassic was plunged into a period of deep, unnatural cold, killing off temperature-sensitive plants and animals. This sudden winter was accompanied by a relentless corrosive acid rain, which poisoned soils and freshwater systems across the globe. This first wave of cold was then followed by a far more prolonged and deadly wave of extreme heat. The same eruptions that released the cooling sulfur also pumped a truly astronomical quantity of carbon dioxide into the atmosphere. This massive injection of greenhouse gases completely overwhelmed the planet's natural carbon cycle. The reflective haze of the volcanic winter eventually rained out of the atmosphere, but the carbon dioxide remained. A powerful, runaway greenhouse effect took hold. Global temperatures soared, swinging from a deep freeze to a sweltering hothouse in a geological instant. The arid landscapes of the Triassic grew even hotter and drier, placing immense stress on the terrestrial ecosystems. The oceans, too, were thrown into chaos. As they absorbed the massive excess of atmospheric carbon dioxide, they became progressively more acidic. This change in water chemistry was devastating for marine life. The reef systems that had just begun to recover from the last great extinction collapsed once more. Countless species of shelled creatures, from the coiled ammonites to the common bivalves, found it impossible to build their calcium carbonate shells in the corrosive water. This collapse at the base of the food chain led to the second great marine extinction of the Mesozoic era. This 1-2 punch of a sudden, freezing winter, followed by a prolonged baking heat, combined with the poisoning of the oceans, acted as a great selective filter on life. The victims were numerous and specific. On the land, the last of the large, labyrinthodont amphibians were wiped out. The advanced, mammal-like cynodonts and other remaining synapsid groups suffered immensely, with only their smallest, most adaptable forms managing to survive. But the most significant casualties were the dominant reptiles of the Triassic, the crocodile-line archosaurs, the mighty Rawassekian predators, the armored Adasaurs, and the aquatic phytosaurs were almost completely annihilated. The ruling dynasty of the Triassic was gone. The top of the food chain, on both land and in the water, was now vacant, and through this gauntlet of fire and ice, heat and acid, the dinosaurs passed, relatively unscathed. Their survival, where their chief competitors failed, was likely due to a suite of key adaptations that made them uniquely resilient. Their probable high metabolism and the insulating coat of primitive, filament-like feathers that many early dinosaurs likely possessed would have helped them to thermoregulate, to survive both the initial, shocking cold and the subsequent, searing heat. And most critically, their highly advanced, bird-like respiratory system, with its network of air sacs and its efficient, one-way flow of air, would have been a massive advantage in the fluctuating, often oxygen-poor and carbon dioxide-rich atmosphere of the extinction's aftermath. They were simply better equipped to handle a world in crisis. And so, we arrive at the dawn of the Jurassic period. 201 million years ago, the world is an empty stage. The Great Extinction has acted as a final, decisive clearing of the board. The dinosaurs' primary competitors for every major terrestrial ecological niche are gone. As the rifting of Pangaea continues, the climate becomes wetter and more stable. The arid deserts are replaced by spreading forests of conifers and cycads. Into this new, green, and empty world, the dinosaur survivors began to radiate with explosive speed and diversity. This was the beginning of the true age of dinosaurs. The three great dinosaur lineages, now freed from all competition, began their conquest of the planet. The carnivorous theropods, which had been mid-sized predators in the Triassic, now evolved to become the new apex predators. A creature like Dilophosaurus, with its distinctive pair of fragile head crests, was one of the first of these new large carnivores. The herbivorous sauropodomorphs, which had already been experimenting with larger sizes, now took the path to true gigantism. Freed from the competition of other large herbivores, they evolved into the first colossal, four-legged sauropods, like Volcanodon, their bodies already adapting with the pillar-like legs and lightweight, air-filled vertebrae that would allow their descendants to become the largest land animals of all time. And the third great group, the ornithischians, began their own diversification, with creatures like the armored Celutosaurus appearing, a blueprint for the great stegosaurs and ankylosaurs to come. The dynasty had finally taken the throne. The world now, and for the next 135 million years, belonged to them.